Hi everyone. So today I will be going through chapter 10, lesson 2. Things that we will be looking at again, I will go through firstly some more analysis of circuits that include both series and parallel combinations, and analysis of circuits that contain more than one source of EMF. I'll do a couple of examples of each, and then I will move on to internal resistance, what we mean by it, how to apply it, what terminal PD and loss volts mean, how to derive the equations that you see here, and how to investigate it, how you can do an experiment basically. It's also one of the PAGs, one of the required practical work that you do need to know. So I will go through techniques and procedures that you can be used to determine the internal resistance. So the first bit I will start with is an example of how to analyze circuits with series and parallel combinations. So if we're given this diagram in an exam, so this is the question. You're given this diagram, you're told calculate the current in, the potential difference across, and power rating for each resistor and in total. Now firstly, I know the total energy. I will use a different color to solve this. So this is the black color, shows the values that were given in the exam, and then you have to calculate current, potential difference, power rating for each resistor and also in total. So I will use blue to show my working out from here on. I already know that the energy given in per unit charge is 12 volts because my EMF, electromotive force, which is once again not a force, is the energy of the power supply per unit charge. I'm given the resistance of each resistor. Since I am given the total energy per unit charge given, so this is the total energy per unit charge. So in other words, the total potential difference that I will have in the circuit. I can also calculate first the total resistance, so I can get the total current going through from the power supply, coming from the power supply, well, in this case, the battery, using a simple equation which you already know. So I know that the total voltage, VT, is 12 volts. I need the total resistance of the circuit so I can get the current coming out of the power supply. So I need to get I total, which is one of the calculations that I need anyway. So I have a combination of series and parallel combination of circuits. I will start by breaking that down. So I will first work with the parallel combination here, which be 1 over R total is equal to 1 over 12 plus 1 over 36, which is 1 over 9. And if I flip both expressions, it will be R total is equal to 9 ohms. So these two resistors together have a total resistance of 9 ohms, which means now I have my 31 ohm resistor in series with a 9 ohm total resistance of those two resistors. So this is a simple circuit, R total, since the series is R1 plus R2, which is 31 plus 9, which is a total of 40 ohms. So the total resistance in my circuit is 40 ohms. So now I need to calculate the total current, which I can do by rearranging my equation. That will be 12 divided by 40, which is 0.3 amps. So the total current I have already calculated it is 0.3 amps. Now if I follow through my diagram, I know that the current will continue to go straight and there's only one path through the first resistor, the 31 ohm resistor. So the current through this resistor is 0.3 amps. So I know the current and I know the, so I'll just move it there. I know the current and I know the resistance of this resistor, so I can calculate the potential difference across it. That will be I times R, using again Ohm's law. So far what I have been using, and the things that you should be always using, is Kirchhoff's first law, Kirchhoff's second law. You need Ohm's law, which is this. You might also at times need to use these equations depending on what the question is asking you to. So these are the very important parts to be able to use to analyze any circuit. And obviously the combination of resistors, don't forget that. So R total in the circuit and how you can calculate that. So moving on from here, the voltage across the 31 ohm resistor should be 0.3 times 31, which gives us 9.3 volts. So I already know from Kirchhoff's second law that if I follow through this path, so I have one loop here and I have another loop here. So the sum of EMF should be equal to the sum of the PDs across a closed loop. So the EMF is 12, and then I have, for the yellow loop, I know that I have, I already calculate 9.3 volts across the 31 ohm resistor. So how much potential difference will be across the 12 ohm resistor? So just simply take away 9.3 from 12. I'll give you 2.7. volts across the 12 ohm resistor. But since it's in parallel with the 36 ohm resistor, and the equation will be the same as well for the 36 ohm resistor, then both of them have 2.7 volts across them. So this component will be, 2.7 volts. This one also will be 2.7 volts. If you go around the loop as well, the green loop, you'll notice it that that's going to be 9.3 plus 2.7. It comes up to 12 either way. So I've calculated the potential difference across each resistor. I know the total potential difference in the circuit already because they gave it to me. I've calculated the total current in the circuit, and I've calculated the current going through, which is the same as the total current going through the circuit. Now I need to calculate the current going through the 12 ohm resistor and the 36 ohm resistor. Since they both have the same potential difference, I know that, let me go to it. So this component here, this resistor and this resistor, have the same potential difference across each one of them. So they get the same amount of energy per unit charge. But since I know R is V over I, and potential difference is the same, for both of them, if I increase the resistance, that means current drops. So I should get a smaller current for the 36 ohm resistor than the 12 ohm resistor. And I also know from Kirchhoff's first law that as soon as current enters this junction, it should split. So 0.3 amps would split in different portions, depending on the resistance of each path. So I know that I can calculate easily current because I have the resistance and the voltage of each of those resistors. So I will calculate the current across the 12 ohm first, which will be V over R. Potential difference across the 12 ohm is 2.7 volts, and its resistance is 12. So that gives me 0.225 amps for the first one. And then I will go to the other one, the 36 ohm resistor, which has a potential difference of 2.7 volts divided by 36, which gives us 0.075 amps. Now if I double check it, 0.225 plus 0.075 gives me 0.3 amps, which means I'm correct in terms of my calculations. That's the total current entering the junction, and it splits in different portions. So I have calculated the current in each resistor, the potential difference across each, the total of current and potential difference in the circuit, and I just need the power rating. Since I already know the current and the potential difference across each component, I can simply use P is equal to VI. So for resistor, for the 31 ohm resistor, it's going to be 9.3 volts times the current, which is 0.3. So this is for the 31 ohm resistor. Which gives 2.79 watts. Power rating of the 12 ohm resistor will be 2.7 times the current through it, which is 0.225. Which gives us 0.6075 watts. And so we can approximate some of these values, by the way, to two significant figures because we're not given better values. So this will be roughly 2.8 watts. This is about 0.61 watts. And then for the last resistor, it's 2.7 times 0.075, which gives us about 0.2 watts. And if I want to know the total rating of all of them, I just add all three together. And I'll get the answer of about 3.5. No, 3.6. So that's a simple analysis of a circuit. I know it might look a bit complicated, but as long as you constantly label in your diagram with the new values that you calculate, it will be easy to figure out. I will do another example, but this case with two power sources and another one as well that's going to be a little bit harder, and that will be it for analyzing circuits in terms of this lesson. So this is another example of analyzing a circuit. If the question gives me this diagram and I have to calculate, for example, the resistance of resistor A, C, and D, and the current going through each component as well, then I should be able to analyze this circuit. So to start with, we already know that we have two different sources of EMF, and since the polarity is the same, so we have positive, negative, positive, negative, positive, negative, and so on. They're all aligned in the correct polarity. So the sum of EMF should be 20 plus 16. If this battery here, with these batteries here were reversed in the other direction, so it will be negative to positive, then I will have to subtract because it's in the opposite direction. So I have to consider the polarity when I take the total EMF. In this case, it's in the same direction, so we have 36 volts of total EMF in the circuit. Then I'm shown that the power of resistor A is 30 watts. So it's telling me that the power of this resistor here is 30 watts. That means if I have V or I can calculate how much that will be, but I don't have anything yet, so I'll have to look at my diagram and figure out where I can work from. Then it tells me that 0.5 amps is going through to this direction. So resistor B and resistor C have 0.5 amps of current going through them. I will just label it on top of each one so I know that I have current for each one. This is using Kirchhoff's first law, remember that. There is no other path for current to take, so it should be the same through resistor B and C. But it won't be the same through resistor D because there's another path for that and we don't know the resistance, so we can't assume that they're equal. So I already can see from here that for resistor B, I have the resistance and I have the current. So I can calculate the potential difference across resistor B, which will allow me to figure out using Kirchhoff's second law the potential difference across resistor A as well. So resistance of B is 20 ohms. Current through B is 0.5 amps. And I need to find VB, which will be I times R, which is 20 times a half, which is 10 volts. So the potential difference across resistor B is 10 volts, so I'll label that there. And the potential difference across C, which is already given to me, is 6 volts. So both resistor B and C together have a total potential difference of 16 volts across them. So between this point and this point, I apply Kirchhoff's second law, which says that the sum of potential difference should be equal to the sum of EMF. But then I also have another resistor here. That means that if this is 10, that's 6, that's 16 in total. But I know that my EMF, my sum of EMF across a closed loop is 36 volts, which means that 36 is equal to the potential difference across B plus the potential difference across C plus the potential difference across A. So if I rearrange, that leaves me 36 minus 16. So the potential difference across A should be 20 volts. Also, since I also know that the potential difference between here and here is 16 volts, then the potential difference across D will also be 16 volts, plus the 20 of the resistor A, and that's 36 in total as well. So I have two loops, one passing from resistor B, C, and going back to the EMF, and another loop going from resistor A, resistor D, and back to the EMF sources. So I figured out the potential difference of each component, which is perfect, because that will help me calculate either current or resistance. We already seen here that the power is 30 watts, so the power of resistor A is 30 watts. The potential difference across it, we calculated it as 20 volts. That means I can calculate the current through A, which will help me calculate the resistance through it. There's two ways of doing it. You can use either equation. I'll show you both. So it's going to be V over R across, you have power of A is equal to VA times IA. So I can rearrange for I, which leaves me with P over VA, which is 30 divided by 20, which is 1.5 amps. So I know that the current now going through the whole circuit is 1.5 amps. And that's the current that goes through resistor A as well. So now from here, I can use V and I to calculate the resistance of resistor A. Or alternatively, I could have used power is equal to V squared over R and calculated the resistance directly for resistor A. But I prefer to have the current because then I can use the current to figure out how much current goes through resistor D, since I already know how much current goes through resistor C either way. So I would just simply use, so this is another way of doing it. I didn't follow that way. I prefer to know my current in my circuit first. Resistance of A is equal to V of A over I of A. And that will be, what was the V of A? That was 20 volts divided by 1.5. Which gives 13.3 ohms. Or in other words, just 13 ohms. If I go to the next part, so I already know the I calculated the resistance of A. I already know the resistance of B, so I need to calculate the resistance of C. I know the potential difference across the 6 volts divided by the current across it, which leaves me with 12 ohms. So I already figured out the resistance of C, and I'm left with only need to find the resistance of D. So since I know that the current going in is 1.5 amps, 0.5 amps of that went upwards, that means the other one will go to resistor D, which using Kirchhoff's first law, we have 1.5 going in, half went out, so that leaves you with 1 amp going through a resistor D. So RD is equal to 16 divided by 1, which is 16 ohms. So through using Kirchhoff's first, second law, Ohm's law, and equations for power that link current and resistance, we figured out all the resistance values. We'll go through one last example. It's a little bit more complicated, and then I will go through internal resistance. Okay, so this can be considered as a very hard example to begin with, but once you get the concepts down right, you'll be fine. So this is the question. Calculate I1, I2, and I3 in the above circuit. Now, in the above circuit, we're given the directions of current in and out. We're also given the EMFs of each power supply or cell given to us. So we need to come up with certain expressions using firstly Kirchhoff's laws. So with Kirchhoff's first law, we know that the current going into a junction is equal to the current coming out of a junction. So into this junction, we have I1 and I2 going in. So I1 plus I2 should be equal to the current coming out, which is I3. So this is Kirchhoff's first law. Now for Kirchhoff's second law, we have to come up with 3 different expressions because we have 3 different loops if we take a quick look at it. I will label it on the diagram and then I will remove it so that I don't make it too messy. So from positive, conventional current goes from positive to negative. So that's loop A. Positive to negative. Loop B. And then I have the bigger loop of both circuits together. Loop C. Okay. I will erase this from the diagram so that it's easier to analyze. I will talk about it, but just to remind you, but these are the 3 loops that we will be looking at. And what I care about loops, because Kirchhoff's second law says that the sum of EMF is equal to the sum of the potential difference across a closed loop. So I have 3 loops to analyze. And we need to always consider the positive and negative directions if the polarity is reversed or doesn't face each other, to make sure that I apply it correctly. So I will start with loop A first. So I labeled loop A to be on this side. So we have the sum of EMF, which is 20 volts. In this case, that's the EMF source, only for loop A. Loop A again, as I remind you, loop A is this loop here. So this is my EMF, which should be equal to the sum of the potential differences across a closed loop. So the potential difference across here plus the potential difference across here. So I will write it in terms, since we know that potential difference is equal to IR, I will write it down in terms of I and R for this resistor. So it's going to be I1 R1 plus I3 R3. So just to remind you again, this is the sum of EMF, which is equal to the sum of the potential difference across this component, which is I times R, plus the sum of the potential difference across this component for loop A. So let me write down here, loop A. I'm going to put the resistance values in there so that it makes it into a proper expression. So that will be 20 is equal to 20 I1 plus 40 I3. So that's loop A. Now going to loop B. Just to remind you again, loop B starts from here, goes around this way, so from positive to negative again. So we have the EMF, which is 30 volts, is equal to the PD of resistor 2, so that's I2 times R2. R2 is 30 ohms, so I will simply write it as 30 I2 plus the potential difference across this resistor. So remember, this is the loop I'm looking at. So that will be plus 40 R3. And then for loop C, so the bigger loop that we talked about, so the big loop from here all the way around to here. So basically we're ignoring the middle part of the whole circuit, but that middle part has been taken account into loop A and loop B either way. So what I have is 20 volts for sum of potential difference plus minus 30 volts because it's in the opposite direction. So you have positive to positive, which means they're facing in different direction. You have to take them away. So that will be 20 minus 30 for the sum of EMF. Once again, remind you, this is the second Kirchhoff's second law. And then we do the sum of potential differences. I only have 2 components in between the EMF, so a resistor 1 and resistor 2. Going all the way around is nothing else. So that will be 20 I1 plus 30 I2. Just to simplify it, is minus 10 is equal to 20 I1 plus 30 I2. So I have 1, 2, 3, 4 expressions. Now if you look at the equations 2, 3, and 4, you have I1, I2, and I3 included in different combinations. Oops, I just realized I wrote down a wrong symbol here. This was supposed to be I3. I always do this mistake. I say one thing and I write another. So yeah, they all have I1, I2, and I3 together in mixed combination. But I prefer to, by having 3 different unknowns, I can use equation 1 to make it two unknowns and hence use simultaneous equations to solve it. Now, like I said, this is a harder end question and might never pop out an exam, but it might do as well. So I will write every I3 in terms of I1 and I2, since I know that Kirchhoff's first law, I3 is equal to I1 plus I2. So I will make my new equations. I'll start with the loop A1, which is going to be 20 is equal to 20 I1. So equation 2 basically. Plus 40, and now I have I3 here. I will replace it with I1 plus I2. So that leaves me with 20 is equal to 20 I1 plus 40 I1 plus 40 I2. That means 20 is equal to 60 I1 plus 40 I2. Then if I look at loop B, so looking at loop B, so equation 3, it will become 30 is equal to 30 I2 plus 40 times I3 needs to be replaced here by I1 plus I2. So that's 30. So I will combine the two common values, which is 30 is equal to 70. I'll actually write I1 first, so 40 I1 plus 70 I2. So now I have equation A and equation B, as well as equation C here, where they're all linked to I1 and I2. I need all of my expressions to include the same unknowns so I can be able to cancel them out. Okay, so I will leave this video, I will leave this example here for now because the analysis after it is simpler. I will move on to internal resistance and what happens, but the idea is that you get a good close attention to what happens to Kirchhoff's first and second law if you have a complex circuit that you don't know where to start from. So you consider the different loops that exist, you analyze it through there. Probably these won't come up in an exam, but it's a good thing to have in mind with so many unknowns, obviously. But it could be possibly coming up with some unknowns, so it's I1 and I2 being unknown or something like that. So be aware of that. So we're gonna go through we're gonna have a look through internal resistance now. Hopefully it will be short and not too long. I know the video is quite long, but it's all about analyzing circuits. Okay, so we start first with what internal resistance is. Now, every source of EMF has internal resistance, meaning a battery, a cell, power supply. They all have internal resistance, and that's the resistance to electric current of the materials inside those sources of EMF, whether it be chemical due to chemical reactions, due to the wires inside the power supply or components within a power supply. So what you have is the energy, when the current flows, energy is transferred to these materials, resulting in energy being lost within the power supply. So we have to take it into account. In a lot of questions, you might see that the internal resistance is negligible, meaning that there's no internal resistance that will affect our calculations. But in certain questions, it will make it very explicit that you do have internal resistance, and then you will need to be able to analyze that. So we always have current flowing, and when there's a current flowing in the power source as well, work has to be done by the charges as they move through the power source. Meaning that, for example, in a cell that you have chemical reactions, the work done is due to these reactions between the chemicals. In solar cells, it is due to the resistance of the materials of the cell. The same thing goes for power supplies. So when we draw internal resistance in a circuit, it should look like this. So we have the power supply, or in this case we have a cell. It's connected in series with a resistor that has a small r that represents internal resistance, because the resistance is within the power supply. So if we have an EMF, for example, of, I don't know, let's say 12 volts. Now, if there is an internal resistance in a circuit, that means that not all these EMFs, so all the energy transferred to each unit charge would be actually less than what's available to the rest of the circuit. So if the internal, if I placed a voltmeter at the terminals of a power supply for a complete circuit, my potential difference measured across those terminals will be less than 12 volts, because some energy already got lost within the power supply. So when you do draw the diagram, you need to include this dashed line around it, this dashed box around the cell and the internal resistance, to show that this includes internal resistance, with a small r for the internal resistance. So if I have 12 joules if I give to each unit charge 12 joules of energy, some of that energy per unit charge will be lost in the internal resistance, which means that less is available to the rest of the circuit. So it could be just that you have, 11.3 volts across it. We call this the terminal potential difference. So the amount of energy per unit charge that will be given to the circuit, and then we have the lost volts in the internal resistance, where is the energy per unit charge wasted, basically. So this is terminal potential difference. So if I use Kirchhoff's second law and apply it to this equation, to these quantities that I already defined, then I have the sum of EMF is equal to the sum of potential differences across a closed loop. So that will be the EMF is equal to the terminal potential difference plus the lost volts. So we want to go to the mathematical form of this equation. Terminal potential difference is given by just V plus the lost volts. So we know V is equal to IR. So I will write it in terms of small r though, because we said that the internal resistance is represented by small r. So plus IR, we come up with an expression like this. And also for the terminal potential difference, I can rewrite it as capital I, capital R, plus IR. And then I can take I as a common factor. So I have a lot of expressions that I can use depending on what I'm given and depending on what I need to use. The same thing applies, the same combination of resistance applies to internal resistances too. So if I wanted to have a lower internal resistance for a power supply, I can connect two cells parallel to each other. If I want them to have a higher internal resistance, I connect them in series. So we deal with internal resistance the same way that we'll deal with normal resistance as well. So let's go back and check our checklist or outcomes. So we talked about internal resistance, terminal potential difference, and lost volts, and how to get to the equations of calculating internal resistance and how they link together. So we'll do an example before I go to the analysis or how to design an experiment, how to analyze it. So here is asking me to calculate first VR, then the amount of lost volts, and then the EMF of the cell. To start with, I'm given the internal resistance, I'm given current, given the resistance of the external resistor, and I'm also shown that there's a voltmeter connected across the resistor. So in other words, VR is the terminal potential difference. And I know that there is a current of 0.8 amps going through the resistor. So if I have resistance and current going through the resistor, I can calculate the potential difference across it. So that will be VR is equal to I times R, which is 0.8 times 1,200. And that should give me about 960 volts. So this is the terminal potential difference. So what the cell allows for the rest of the circuit to have across it. Then it's asking me to calculate the lost volts. Now once again, I have the current going through the cell, and I also have the internal resistance going through the cell. So for B, it will be lost volts is equal to I times the internal resistance, which is 0.8 times 15, which is 12 volts. And it tells me to calculate in C the EMF of the cell. So we already said that the EMF of the cell is the terminal potential difference plus lost volts. So EMF is the terminal potential, which is 960, plus the lost volts, which is 12. So the cell has 972 volts of EMF. As you can see, the cell, even though it has 972 volts, it cannot provide that to the rest of the circuit because the internal resistance takes away some of that energy per unit charge just to oppose the motion of current through the actual power supply. So the whole circuit doesn't get the full energy because some of it gets lost. That's why we call it lost volts within the power supply. So the experiment to investigate internal resistance is quite simple. All you need is a power supply, like a cell, for example. Connect a voltmeter to the terminals of the cell, an ammeter in series with a variable resistor, so you can adjust the resistance of the circuit, which will give you different values for current and potential difference. And we will be recording current and potential difference in this equation, in this experiment. So connect the circuit as shown in the picture, vary the resistance using variable resistor, and record V and I at different resistances. So we will record the potential difference at different values of current, and then we can plot to analyze the experiment and get the internal resistance. We need to plot a graph of V against I. So it should be a graph that looks like this. We know that our equation is EMF is VI, RI, capital RI. Let me restart that. So EMF is the terminal potential difference, which is recorded by the voltmeter across the terminals of the cell. Alternatively, we could have placed the voltmeter across the variable resistor, which will give us the same values anyway, plus the current times the internal resistance. So this is the relationship that we know involves internal resistance. Now if I'm plotting V against I need to, because this is the equation of a straight line, y is equal to mx plus c. I want to rearrange my equation to look similar to this. Now the y-axis value is the potential difference, the x-axis is the current. So I will rearrange my expression to look similar to the equation of a straight line. That means V should become the subject of the formula. That will be V is equal to minus IR plus EMF. So write this below this equation. Which means I have now my Y value is my potential difference, my X value is the current, my Y-intercept will be the EMF, so the energy provided by the circuit per unit charge, and my gradient will be my internal resistance, but will be a negative gradient. So what you would expect to have a Y-intercept, which is your EMF, and you would expect a straight line that's got a negative slope. So if you calculated the gradient, so the change in y over the change, so gradient is the change in y divided by the change in x, which is going to be equal to your internal resistance. And remember to get the biggest triangle for the gradient. Now, a few things about the graph. If I doubled the value of EMF or even increased the value of EMF and I had the same resistance, what I would expect is a graph that has a higher EMF, but the same gradient since the internal resistance is the same, so it will be shifted upwards. Now, if I had the same EMF, but I doubled the internal resistance, then I should expect a graph that's steeper but the same EMF. So something like this roughly. So it's all about figuring out which value gets affected. So if it's the y-intercept affected and the gradient doesn't, so the internal resistance is constant, then you follow something that goes up or down with the same gradient line. If the internal resistance is affected but the EMF is not, then you have to leave the EMF where it is and see how that will affect the gradient of the line. Okay, so now going back to the learning objectives, we have looked at analyzing circuits with components. We have looked at multiple sources of EMF. We talked about the techniques and procedures used to determine the internal resistance of a chemical cell or other source of EMF and how to analyze it. If you have any questions, do let me know. Make sure you understand the difference between EMF, terminal, PD, and lost volts. If you don't, let me know in class or in the comments or whatever you want from or through Teams, and we can go through it again. Hope this helps and see you next time.